What I'm about to show you shouldn't exist. According to everything we know about physics, astronomy, and the fundamental laws that govern our universe, what you're looking at is impossible. Yet there it is, captured by the most powerful telescope ever built, staring back at us like a cosmic middle finger to our understanding of reality. This tiny dot of light, barely visible even to the James Webb Space Telescope, has just shattered 50 years of astronomical theory. It's a galaxy that breaks every rule we thought we understood about how stars, gas, and gravity work together. It's showing us light that has no right to exist, behaving in ways that make our best physicists scratch their heads in bewilderment. The galaxy has a name, GSNDG 9422, but NASA scientists have a simpler term for it. They call it weird. Not just unusual, not just unexpected. Weird. Because in this galaxy, gas is outshining its stars, something that should be physically impossible. To understand why this discovery is so earth-shattering, imagine walking into your house and finding that your lampshades are brighter than the light bulbs inside them. That's essentially what we're seeing in this galaxy, and it's making astronomers question everything they thought they knew about how the universe works. But here's what will terrify you. This isn't just some quirky cosmic oddball. This galaxy may be a missing link phase of galactic evolution between the universe's first stars and familiar, well-established galaxies. It might be showing us a phase of cosmic evolution that we never knew existed, a phase that could rewrite the story of how everything in the universe came to be. This galaxy exists approximately 1 billion years after the Big Bang, a time when the universe was still a cosmic infant, when the first generation of stars were just beginning to light up the primordial darkness. What we're seeing might be a snapshot of cosmic evolution frozen in time, preserved by the speed of light across 13 billion years of space. The implications are staggering. If this galaxy represents a missing link in cosmic evolution, it means our understanding of how the universe grew from simple hydrogen and helium into the complex cosmos we see today has been fundamentally incomplete. We've been trying to solve a puzzle with missing pieces, and this galaxy might be the piece that makes everything else make sense. To understand the magnitude of this discovery, you first need to understand the incredible machine that made it possible. The James Webb Space Telescope isn't just an upgrade from Hubble, it's a complete revolution in our ability to peer into the deepest reaches of space and time. Launched in December 2021 after decades of development and delays, Webb is positioned at a point in space called L2, about 1.5 million kilometers from Earth. From this vantage point, it can observe the universe without interference from Earth's atmosphere, heat, or reflected sunlight. Its massive 6.5-meter mirror, nearly 3 times larger than Hubble's, collects light with unprecedented precision. But Webb's real superpower isn't its size. It's its ability to see in infrared light. When light travels across billions of years of expanding space, it gets stretched by the expansion of the universe itself. What started as visible light from the first stars and galaxies has been redshifted into infrared wavelengths by the time it reaches us. Webb can see this ancient light that's invisible to human eyes and most other telescopes. This makes Webb essentially a time machine. The farther it looks into space, the farther back in time it sees. When Webb observes a galaxy 13 billion light-years away, it's seeing that galaxy as it was 13 billion years ago, when the universe was just 800 million years old. It's like having a window into cosmic history, allowing us to watch the universe's childhood unfold before our eyes. Webb's instruments are so sensitive that they can detect the heat signature of a bumblebee at the distance of the moon. They can analyze the chemical composition of exoplanet atmospheres, study the formation of the first stars, and peer into stellar nurseries where new worlds are being born. Every observation reveals details about the universe that were previously impossible to obtain. The telescope operates at incredibly cold temperatures, about 50 Kelvin above absolute zero, to minimize thermal interference with its sensitive infrared detectors. Its sun shield, the size of a tennis court, keeps it in perpetual shadow while its instruments work with precision that borders on the miraculous. But even with all of Webb's incredible capabilities, nobody expected to find something like GSNDG 9422. The galaxy appeared in Webb's deep field observations as part of a systematic survey of the early universe. And at first glance, it looked unremarkable. Just another faint dot among thousands of distant galaxies. It was only when astronomers analyzed the light spectrum from this galaxy that they realized they were looking at something unprecedented. The spectral signature, the cosmic fingerprint that tells us about the galaxy's composition and properties, was unlike anything they had ever seen before. Understanding why GSNDG 9422 is so shocking requires understanding how galaxies normally work. In every galaxy we've ever studied, from our own Milky Way to the most distant systems Webb can observe, the same basic rules apply. Stars are the primary sources of light, and gas clouds shine only when they're illuminated by nearby stars. Think of it like a cosmic cityscape. Stars are like streetlights shining with their own energy from nuclear fusion in their cores. Gas clouds are like buildings. They can reflect and scatter starlight, sometimes creating beautiful colors and structures, but they don't generate their own light. The brightest things in any city are the streetlights themselves, not the buildings they illuminate. This fundamental relationship exists because of the physics of light and matter. Stars generate enormous amounts of energy through nuclear fusion, converting hydrogen into helium and releasing photons across the entire electromagnetic spectrum. These photons travel through space and can ionize nearby gas atoms, causing them to emit light at specific wavelengths. But the light from ionized gas is always fainter than the light from the stars that ionize it. It's a reflection process. The gas can never be brighter than its energy source. It's like expecting a mirror to be brighter than the light shining on it. The physics simply doesn't allow it. GSNDG 9422 stood out because it has an odd, never-before-seen light signature, indicating that its gas is outshining its stars. When astronomers analyzed the spectrum, they found that the emission lines from ionized gas were stronger than the continuum emission from stars. The buildings were brighter than the streetlights. This spectral signature is what researchers call a totally new phenomena. In all the decades of astronomical observation, across millions of galaxies studied with ground-based and space-based telescopes, nothing like this had ever been detected. It challenged the most basic assumptions about how galaxies work. The discovery was so unexpected that the research team spent months double-checking their data, looking for instrumental errors or calibration problems. They ran the analysis multiple times, used different techniques, and even had other research groups independently verify the results. Every analysis came to the same impossible conclusion. The gas in this galaxy is somehow outshining its stars. The research team's reaction was summed up by one astronomer who simply said, "That's weird." But weird doesn't capture the magnitude of what they were seeing. This wasn't just unusual. It was physically impossible according to everything we thought we knew about stellar and galactic physics. As astronomers tried to understand what they were seeing, a revolutionary possibility began to emerge. Galaxy GSNDG 9422 may be a missing link phase of galactic evolution between the universe's first stars and familiar, well-established galaxies. It might represent a transitional phase in cosmic evolution that we had theorized about but never directly observed. To understand why this is so significant, we need to go back to the very beginning of cosmic history. In the first few 100 million years after the Big Bang, the universe was a very different place than it is today. There were no galaxies as we know them, no planets, no complex chemistry, just vast clouds of hydrogen and helium gas slowly collapsing under their own gravity. The first stars to form in this primordial universe were unlike anything we see today. Astronomers call them population 3 stars, massive, pure hydrogen and helium giants that burned incredibly hot and bright. They are hypothetical, massive stars formed in the early universe and thought to contain only hydrogen and helium. These first stars were cosmic alchemists, fusing light elements into heavier ones for the first time in the universe's history. When they died in spectacular supernova explosions, they scattered these newly created heavy elements, carbon, oxygen, silicon, iron, into the surrounding space, seeding the universe with the raw materials needed for planets and life. But here's the problem. We've never directly observed population 3 stars. They lived and died so long ago that their light hasn't had time to reach us yet, or they're too faint and distant for even our most powerful telescopes to detect. Our understanding of this crucial phase of cosmic evolution has been entirely theoretical. GSNDG 9422 might be the bridge between this theoretical past and the observed present. It might represent a phase of galactic evolution when the first heavy elements created by population 3 stars were just beginning to influence how new stars formed and how galaxies evolved. It could be showing us the moment when the universe transitioned from its primordial simplicity to the complex cosmic ecosystem we see today. If this interpretation is correct, then the strange properties of GSNDG 9422 aren't a violation of physics. They're a window into a phase of physics that we've never observed before. The galaxy might be operating under conditions that no longer exist anywhere in the modern universe, following rules that applied only during the cosmic dawn. The key to understanding GSNDG 9422 lies in its spectrum, the breakdown of light into its component wavelengths that reveals the physical conditions in the galaxy. The strange spectrum of galaxy GSNDG 9422 is likely coming from its superheated gas, not its stars. But this raises more questions than it answers. Normally, when we analyze a galaxy's spectrum, we see a combination of stellar continuum emission, the smooth background of light from stars, and emission lines from ionized gas clouds. The stellar continuum is usually much brighter, with gas emission lines appearing as spikes on top of the stellar background. In GSND G9422, this relationship is reversed. The emission lines from ionized gas dominate the spectrum, while the stellar continuum is unusually faint. It's as if the galaxy's gas clouds have become independent light sources, generating more energy than the stars that are supposed to be powering them. Together, an observational astronomer and a theorist investigated potential causes for this bizarre spectral signature. They considered every possible explanation within the framework of known physics. Unusual stellar populations, exotic stellar evolution phases, gravitational lensing effects, instrumental artifacts, and even the possibility of observational errors. None of the conventional explanations could account for what they were seeing. The spectral signature was so unusual that it required entirely new theoretical models to explain. The research team found themselves in the uncomfortable position of having discovered something that their existing knowledge couldn't accommodate. The spectrum also revealed other unusual properties. The gas in GSNDG 9422 appears to be extremely hot, much hotter than gas in typical galaxies. The ionization state of the gas suggests temperatures and energy densities that would normally be impossible to maintain without powerful stellar energy sources. Yet the stellar component of the galaxy appears to be unusually faint and cool. This creates a paradox. The galaxy has cool, faint stars, but hot, bright gas. It's like finding a room where the radiators are cold, but the air is scorching hot. Something is heating the gas to extreme temperatures, but that something isn't the stars we can observe. The spectral analysis also revealed hints about the galaxy's chemical composition. Unlike more recent galaxies, which show evidence of multiple generations of stellar evolution and complex chemical enrichment, GSNDG 9422 appears to have a much simpler composition. It might represent an early phase of chemical evolution when the universe's elemental palette was still limited. The discovery of GSNDG 9422 doesn't just challenge our understanding of individual galaxies. It challenges the entire standard model of how galaxies form and evolve over cosmic time. This model, developed over decades of observation and theoretical work, describes a hierarchical process where small structures merge to form larger ones, gradually building up the complex galactic ecosystem we see today. According to the standard model, galaxy formation follows a predictable sequence. First, dark matter halos collapse under their own gravity, creating gravitational wells that can trap ordinary matter. Gas falls into these wells, cools, and condenses into the first generation of stars. These stars live, die, and enrich the gas with heavy elements, enabling the formation of more complex stellar populations. Over time, small galaxies merge to form larger ones, star formation rates evolve, and the chemical composition of galaxies becomes increasingly complex. The process is gradual and continuous, with each phase building on the previous ones in a way that can be modeled mathematically. GSNDG 9422 doesn't fit this model. Its properties suggest that it might represent a phase of galactic evolution that the standard model doesn't account for, a transitional period when different physical processes dominated galactic evolution. If this interpretation is correct, it means our understanding of cosmic evolution has been incomplete. The galaxy's unusual properties might be telling us about physical processes that were important in the early universe, but became irrelevant later on. These could include the effects of the first generation of stars, the initial mixing of heavy elements into the primordial gas, or even exotic physics that only operated under the extreme conditions of the cosmic dawn. Understanding these early phases of galactic evolution is crucial for understanding how the universe evolved into its current state. The galaxies we see today are the end products of billions of years of evolution. To understand how they got to be the way they are, we need to understand the processes that shaped them in their youth. GSNDG 9422 might be providing us with direct observational evidence of these early processes for the first time. It could be the missing piece that helps us understand how the simple hydrogen and helium universe of the cosmic dawn evolved into the complex, chemically rich cosmos we inhabit today. To fully appreciate the impossibility of what we're seeing in GSNDG 9422, we need to understand the physics of how gas clouds in galaxies normally produce light. This process, called photoionization, is one of the most fundamental mechanisms in astrophysics and operates according to well-established physical laws. When high-energy ultraviolet photons from hot stars hit neutral hydrogen atoms in nearby gas clouds, they can knock electrons completely away from their protons, creating ionized hydrogen plasma. This process requires a specific minimum energy, 13.6 electron volts per photon, which corresponds to ultraviolet light with wavelengths shorter than 91.2 nanometers. Only the hottest, most massive stars produce enough ultraviolet radiation to ionize significant amounts of gas. These are typically O-type and B-type stars with surface temperatures exceeding 10,000 Kelvin and masses greater than 8 times that of our Sun. Smaller, cooler stars like our Sun produce very little ionizing radiation and have minimal impact on surrounding gas clouds. Once the hydrogen is ionized, the free electrons can recombine with protons, releasing photons at specific wavelengths determined by quantum mechanics. The most prominent of these is the H-alpha line at 656.3 nanometers, which gives many nebulae their characteristic red color. Other hydrogen lines produce light at different wavelengths, creating a distinctive spectral signature. The crucial point is that this is a secondary process. The gas can only emit as much energy as it receives from the ionizing stars. In fact, it emits significantly less because much of the stellar energy is absorbed and converted to heat rather than re-radiated as visible light. The typical efficiency of photoionization is only about 1 to 2%, meaning that even under ideal conditions, gas clouds should be 50 to 100 times fainter than the stars that ionize them. This energy balance is fundamental to our understanding of galactic physics. Stars are energy producers, converting matter into energy through nuclear fusion. Gas clouds are energy processors, converting high-energy ultraviolet photons into lower-energy visible photons. The second law of thermodynamics requires that energy can only flow from higher to lower energy states, never the reverse. In every galaxy we've studied, this relationship holds true. Star-forming regions, planetary nebulae, and supernova remnants all follow the same pattern. They shine because they're illuminated by nearby stars and they're always fainter than those stars. The physics simply doesn't allow any other possibility. Yet GSNDG 9422 seems to violate this fundamental principle. Its gas emission is stronger than its stellar emission, suggesting that the gas is somehow producing more energy than it's receiving from stars. This violates our understanding of energy conservation and thermodynamics on a cosmic scale. One of the leading theories to explain GSNDG 9422's impossible behavior involves the universe's first generation of stars. Population 3 stars are hypothetical massive stars formed in the early universe and thought to contain only hydrogen and helium. These primordial giants could have properties dramatically different from any stars we observe today. Without heavy elements to facilitate cooling, the first gas clouds in the universe could only form stars under very specific conditions. Computer simulations suggest that population 3 stars were typically much more massive than modern stars, perhaps 100 to 1,000 times the mass of our Sun, because the primordial gas couldn't fragment into smaller pieces as easily as metal-enriched gas. These massive primordial stars would have burned incredibly hot and bright, with surface temperatures possibly exceeding 50,000 Kelvin, twice as hot as the most massive stars we observe today. They would have produced enormous amounts of ultraviolet radiation, far exceeding anything in the modern universe. More importantly, population 3 stars would have had very short lifetimes, perhaps only a few million years before exploding as supernovae or collapsing into black holes. This means they would have died and disappeared long before the universe developed the complex galactic structures we see today. But what if GSNDG 9422 represents a galaxy caught in the act of transitioning from population 3 to population 2 stars? What if we're seeing the aftermath of the first stellar generation, when the newly created heavy elements were just beginning to change how gas behaves in galaxies? The theory suggests that the supernova explosions of population 3 stars could have created conditions unlike anything in the modern universe. These explosions would have been extraordinarily energetic, potentially injecting massive amounts of kinetic energy into the surrounding gas. The shock waves from multiple supernovae could have heated gas to temperatures of millions of degrees, hot enough to shine brightly in ways that normal stellar heating cannot achieve. This scenario could explain why the gas in GSNDG 9422 appears to outshine its stars. The visible stars might be the second generation, smaller, cooler stars formed from gas that had been enriched with heavy elements by population 3 supernovae. Meanwhile, the bright gas emission could be the lingering afterglow of the population 3 explosions, still glowing from the enormous energy input of the primordial stellar deaths. If this theory is correct, GSNDG 9422 might be showing us direct evidence of population 3 stars for the first time. Not the stars themselves, which would have died billions of years ago, but their cosmic legacy, the dramatic impact they had on their environment that persisted long after the stars themselves were gone. While the population 3 theory is compelling, it's not the only possible explanation for GSNDG 9422's bizarre properties. The galaxy might be revealing physics that we don't yet understand, or familiar physics operating under extreme conditions that no longer exist in the modern universe. One possibility involves active galactic nuclei, AGN, supermassive black holes at the centers of galaxies that can produce enormous amounts of energy as they consume surrounding matter. In the early universe, when galaxy formation was more chaotic and gas-rich, AGN might have behaved differently than they do today. Early AGN could have been more variable and energetic, creating phases of intense radiation that could ionize gas throughout entire galaxies. If GS-NDG-9422 contains an active supermassive black hole, it might be able to ionize gas more efficiently than normal stars, creating the observed spectral signature. Another possibility involves cosmic rays, high-energy particles that can ionize gas through collisions rather than photoionization. In the early universe, with more frequent supernova and more chaotic magnetic fields, cosmic ray densities might have been much higher than they are today. High-energy particles could potentially heat and ionize gas without requiring hot stars. Some theorists have even suggested more exotic possibilities. The early universe might have contained forms of dark matter that interact more strongly with normal matter than modern dark matter does. These interactions could have provided additional energy sources for heating gas clouds, creating the observed spectral signatures without violating known physics. There's also the possibility that GSNDG 9422 is showing us a phase transition in the universe's evolution, a moment when the fundamental parameters that govern galactic physics change from their primordial values to their modern ones. The cosmic microwave background radiation was much more intense in the early universe, providing additional heating that might have affected how gas behaves in galaxies. Magnetic fields might also play a role. The primordial universe could have had much stronger magnetic fields than exist today, and these fields could have affected how gas moves and radiates energy. Magnetohydrodynamic processes in strong magnetic fields can create heating mechanisms that don't exist in weaker field environments. The truth is that we simply don't know what physics dominated in the very early universe. Our understanding is based on extrapolating from conditions we can observe today, but the early universe was so different that entirely new physical processes might have been important. GS-NDG-942 2 might be our first direct observation of these exotic early universe physics in action. Instead of showing us a violation of known physics, it might be showing us physics that we never knew existed, physics that only operated under the extreme conditions of cosmic infancy. Among the more speculative but intriguing explanations for GSNDG 9422 is the possibility that we're witnessing the effects of helium flash events on a galactic scale. Helium flashes are violent nuclear burning episodes that occur in certain types of evolved stars, but they might have had very different consequences in the primordial universe. In modern astronomy, helium flashes occur in low-mass stars during their red giant phases. As these stars exhaust their hydrogen fuel, their cores contract and heat up until helium fusion ignites explosively. The flash releases enormous amounts of energy in a very short time, causing dramatic changes in the star's structure and energy output. But in the early universe, with different stellar populations and chemical compositions, helium flashes might have behaved very differently. The first generation of stars formed from pure hydrogen and helium might have undergone much more violent and energetic helium burning phases than anything we observe today. Computer models suggest that population 3 stars might have experienced multiple, successive helium flashes during their evolution, each one more energetic than the last. These flashes could have ejected massive amounts of energy and material into the surrounding interstellar medium, creating expanding shells of hot, ionized gas. If multiple population 3 stars in a single galaxy underwent helium flashes around the same time, the cumulative effect could have been spectacular. The galaxy would have been flooded with hot, ionized gas that continued to radiate energy long after the original stellar events. This could create exactly the kind of spectral signature we observe in GSNDG 9422. The helium flash hypothesis is attractive because it provides a mechanism for heating gas to extreme temperatures without requiring the stars to still be present and observable. The flashes would have occurred billions of years ago, but their effects could persist in the form of hot, expanding gas shells that are still cooling and recombining today. This scenario also explains why the stellar component of GSNDG 9422 appears relatively normal, while the gas component is so unusual. The stars we observe might be a later generation that formed after the helium flash events, while the bright gas emission represents the ongoing aftermath of those ancient explosions. Testing this hypothesis will require detailed modeling of population 3 stellar evolution and helium flash physics under primordial conditions. It will also require more observations of GSNDG 9422 to determine the detailed properties of its gas and stellar populations. Another class of explanations for GSNDG 9422's unusual properties involves gravitational processes that might have been more important in the early universe than they are today. When the universe was younger and denser, gravitational interactions could have generated heating mechanisms that no longer operate efficiently in the modern cosmos. One possibility is gravitational heating through galaxy mergers and interactions. In the early universe, galaxies were smaller, closer together, and more likely to undergo violent merger events. When two gas-rich galaxies collide, the gravitational interactions can compress and heat their gas to extremely high temperatures, potentially creating the kind of bright emission we observe in GSNDG 9422. The heating mechanism works through gravitational shock waves that propagate through the merging gas. As the galaxies approach each other, their gravitational fields create tidal forces that compress and accelerate the gas. When gas streams from different galaxies collide at high velocities, They create shock fronts that convert kinetic energy into thermal energy. These collision-induced shocks can heat gas to temperatures of millions of degrees, hot enough to radiate brightly across the electromagnetic spectrum. The heated gas remains ionized and continues to radiate energy as it slowly cools, potentially creating the extended bright emission we observe in JWST 9422. Another gravitational heating mechanism involves accretion onto dark matter halos. In the early universe, dark matter halos were still actively growing through the accretion of smaller structures. As gas falls into these growing halos, it can be heated to high temperatures through a process called virial heating. The physics is similar to what happens when you compress air in a bicycle pump. The compression work gets converted into heat. As gas falls into deep gravitational potential wells, it gains kinetic energy that gets converted to thermal energy when the gas is compressed and thermalized in the halo. In the early universe, with actively growing dark matter halos and abundant gas supplies, this virial heating could have been much more intense than it is today. The combination of rapid halo growth and high gas densities could have created heating rates that are impossible to achieve in the modern universe. Cold, dark matter streams might also play a role. Computer simulations show that dark matter flows into halos in narrow, cold streams that can interact with gas in complex ways. In the early universe, these streams might have been more numerous and energetic, creating turbulent mixing that could heat gas through friction and magnetic reconnection. All of these gravitational heating mechanisms have the advantage of being able to heat gas to extreme temperatures without requiring hot stars. They could potentially explain how JWST 9422's gas became bright enough to outshine its stellar population, while still operating within the framework of known physics. The discovery of JWST 9422 isn't just adding a new chapter to our understanding of cosmic evolution. It's potentially rewriting the entire timeline of how the universe developed from its primordial state into the complex cosmic ecosystem we observe today. If this galaxy truly represents a previously unknown phase of galactic evolution, it means our cosmic timeline has been missing crucial chapters. The standard cosmic timeline tells a story of gradual development. After the Big Bang, the universe spent about 380,000 years cooling and expanding until electrons and protons could combine to form neutral hydrogen atoms. This event, called recombination, made the universe transparent to light for the first time, creating the cosmic microwave background radiation we observe today. For the next several 100 million years, the universe entered what cosmologists call the Dark Ages, a period when no stars had yet formed and the universe was filled only with neutral hydrogen and helium gas slowly collapsing under its own gravity. This period lasted until the first stars ignited, beginning the cosmic dawn that ended the Dark Ages and started the process of reionization. The reionization epoch is thought to have lasted from about 400 million to 1 billion years after the Big Bang, as the first stars and galaxies gradually ionized all the hydrogen in the universe. By the end of this period, the universe had developed the basic large-scale structure we see today, with galaxies, clusters, and cosmic voids arranged in the cosmic web. JWST 9422 exists approximately 1 billion years after the Big Bang, placing it right at the end of the reionization epoch. This timing is crucial because it suggests we might be seeing a galaxy that formed during this critical transition period when the universe was evolving from its primordial simplicity to its modern complexity. If JWST 9422 represents a missing phase of cosmic evolution, it implies that our understanding of the reionization epoch has been incomplete. We might have been missing an entire category of galactic evolution that was crucial for understanding how the universe developed its current properties. This missing phase could help explain some of the puzzles in modern cosmology. For example, observations suggest that reionization happened faster than our models predict it should have. If galaxies like JWST 9422 were more common in the early universe, they could have contributed additional sources of ionizing radiation that accelerated the reionization process. The discovery also raises questions about when various phases of cosmic evolution actually occurred. If gas-dominated galaxies like GSNDG 9422 existed a billion years after the Big Bang, it suggests that the transition from primordial to modern galactic physics happened later than we thought, or that it was more gradual and complex than our models assume. Understanding this timeline is crucial for understanding how the universe evolved into its current state. Every phase of cosmic evolution builds on the previous phases, so missing or misunderstanding early phases can lead to incorrect predictions about later evolution. GSNDG 9422 might be forcing us to revise our understanding of this fundamental cosmic chronology. GSNDG 942 may be a missing link phase of galactic evolution between the universe's first stars and familiar, well-established galaxies. This potential role as a cosmic missing link makes it one of the most important astronomical discoveries in decades, because it could help us understand how individual stars evolved into organized galactic systems. The transition from the first stars to the first galaxies is one of the most poorly understood phases of cosmic evolution. We know that population 3 stars form from primordial hydrogen and helium gas, and we know that modern galaxies contain complex populations of stars with a wide range of ages and chemical compositions. But the process by which one evolved into the other has been largely theoretical. The challenge is that this transition happened so long ago and involves such faint objects that direct observation has been impossible until now. We can study the end products, modern galaxies, and we can theorize about the beginning. Population 3 stars. But the intermediate phases have been hidden from us by distance and time. GSNDG 942 might represent one of these intermediate phases. Its unusual properties suggest that it's neither a simple collection of population 3 stars nor a fully developed modern galaxy. Instead, it might be something in between, a system that has evolved beyond the primordial state but hasn't yet developed the complex structure of mature galaxies. This transitional nature could explain many of the galaxy's puzzling features. The dominance of gas emission over stellar emission might reflect a phase when gas physics was more important than stellar physics for determining galactic properties. The unusual chemical composition might reflect incomplete mixing of heavy elements produced by the first supernova. If this interpretation is correct, GSNDG 9422 could help us understand how the universe developed its chemical complexity. Modern galaxies show evidence of multiple generations of stellar evolution, with each generation producing heavier elements that get incorporated into subsequent generations. But how this process started, how the first heavy elements got mixed into the primordial gas, has been unclear. GSNDG 9422 might be showing us this process in action. Its properties could reflect the moment when the first heavy elements were beginning to change how gas behaves in galaxies, but before stellar populations had fully adapted to these new conditions. Understanding this missing link phase is crucial for understanding how complexity emerged in the universe. The evolution from simple hydrogen and helium gas to chemically complex galaxies capable of forming planets and life represents one of the most important transformations in cosmic history. GSNDG 9422 might be our first direct glimpse of how this transformation actually occurred. The discovery of GSDG 942 forces us to reconsider our fundamental understanding of how stars form and how they interact with their galactic environments. If gas can indeed outshine stars in certain conditions, it suggests that our models of star formation and galactic evolution are incomplete in ways we're only beginning to understand. Traditional star formation theory assumes that stars are the primary energy sources in galaxies, and that all other phenomena, from gas heating to chemical enrichment, are secondary consequences of stellar processes. But GSNDG 942 suggests that under certain conditions, gas physics might be more important than stellar physics for determining galactic properties. This could fundamentally change how we think about the early universe. Instead of viewing early galaxies as collections of stars with associated gas, we might need to view them as gas systems with associated stars. The gas, rather than being a passive medium illuminated by stars, might have been an active participant in galactic evolution. This perspective shift has implications for understanding how the first galaxies formed and evolved. If gas processes were dominant in early galaxies, then our models of galaxy formation, which focus primarily on stellar processes, might be missing crucial physics that was important in the cosmic dawn. The discovery also raises questions about the efficiency of star formation in the early universe. If galaxies like GSNDG 9422 were common, they might have been much less efficient at forming stars than modern galaxies. This could help explain some puzzling observations about early cosmic evolution, such as why ionization took as long as it did. GSNDG 9422 represents a new frontier in what astronomers call cosmic archaeology, using observations of distant objects to reconstruct the history of cosmic evolution. This galaxy demonstrates that there are still fundamental discoveries to be made about the universe's past, even with our most advanced telescopes. The James Webb Space Telescope is uniquely positioned to find more objects like GSNDG 9422. Its unprecedented sensitivity in infrared light allows it to detect faint, distant galaxies that were invisible to previous telescopes. As Webb continues its observations, we may discover that GSNDG 9422 isn't unique. There might be an entire population of similar objects waiting to be found. Finding more examples of these unusual galaxies would allow astronomers to study their properties in detail and determine whether they represent a distinct phase of cosmic evolution or simply rare, extreme examples of known physics. Multiple examples would also allow statistical studies that could reveal patterns and correlations invisible in a single object. The discovery also highlights the importance of spectroscopic observations, detailed analysis of light spectra rather than just imaging. While images can reveal the existence of distant objects, only spectroscopy can reveal their physical properties in evolutionary state. GSNDG 9422 would have remained just another faint dot in space without the spectroscopic analysis that revealed its unusual nature. Future observations with Webb and other telescopes will focus on understanding the detailed physics operating in GSNDG 9422. Astronomers want to determine the temperature, density, and chemical composition of its gas, the masses and ages of its stars, and the overall dynamics of the system. The discovery of GSNDG 9422 and its implications for cosmic evolution have profound consequences for understanding how life might emerge and evolve in the universe. If our understanding of early galactic evolution has been incomplete, it means our predictions about when and where life could emerge might also need revision. The formation of complex chemistry necessary for life depends on the production and distribution of heavy elements by multiple generations of stars. Carbon, oxygen, nitrogen, phosphorus, and other elements essential for biology are created in stellar cores and distributed through space by supernova explosions and stellar winds. If galaxies like GSNDG 9422 represent a phase of evolution when this chemical enrichment process was just beginning, they might help us understand how long it took for the universe to become capable of supporting life. The timing and efficiency of heavy element production and mixing could determine when the first potentially habitable worlds could form. The unusual gas heating processes in GSNDG 942 might also affect planetary formation and evolution in ways we don't yet understand. Hot ionized gas environments could influence how planetary systems form and how atmospheric evolution proceeds. Understanding these early galactic environments is crucial for predicting where life might emerge. GSNDG 942's unusual properties might also provide new insights into the nature of dark matter and dark energy, the mysterious components that make up 95% of the universe, but remain poorly understood. The galaxy's formation and evolution occurred during a period when dark matter structures were still actively growing, and dark energy was beginning to dominate cosmic expansion. The heating mechanisms that make GSNDG 9422's gas so bright might be related to dark matter physics in ways we haven't previously considered. If dark matter interacts with ordinary matter more strongly than we currently believe, or if it underwent phase transitions in the early universe, these processes could have contributed to the unusual heating we observe. Similarly, the early dominance of dark energy could have affected how galaxies like GSNDG 9422 formed and evolved. The accelerating expansion of space driven by dark energy would have made it increasingly difficult for gas to fall into dark matter halos and form stars, potentially creating the unusual conditions that led to GSN DG9422's distinctive properties. The discovery of GSNDG 9422 raises profound philosophical questions about the nature of scientific knowledge and our understanding of the universe. How much about cosmic evolution do we still not understand? What other fundamental phases of cosmic history remain hidden from us? The galaxy serves as a humbling reminder that despite centuries of astronomical progress, we're still discovering basic facts about how the universe works. Our understanding of cosmic evolution, which seemed relatively complete just a few years ago, suddenly appears to have major gaps that we didn't even know existed. This discovery also illustrates the importance of expecting the unexpected in astronomy. GSNDG 9422 was found not through a targeted search for unusual objects, but as part of a systematic survey that happened to capture something unprecedented. It reminds us that the universe still holds surprises that challenge our most fundamental assumptions. The philosophical implications extend beyond astronomy to questions about the nature of knowledge itself. If our understanding of something as basic as how galaxies form can be so incomplete, what does this say about the reliability of human knowledge? How can we distinguish between well-established facts and assumptions that might be overturned by future discoveries? As we reach the end of our journey through the mystery of GSNDG 9422, it's clear that this tiny, distant galaxy has opened an entirely new chapter in our understanding of cosmic evolution. What began as a simple spectroscopic observation has revealed fundamental gaps in our knowledge of how the universe developed from its primordial state into the complex cosmic ecosystem we inhabit today. The galaxy's impossible properties, gas that outshines its stars, have forced astronomers to reconsider some of their most basic assumptions about how galaxies work. It has revealed that the early universe was even stranger and more complex than we imagined, operating according to physical processes that no longer exist in the modern cosmos. Whether GSNDG 9422 represents a missing link in cosmic evolution, evidence of exotic physics, or a window into the aftermath of population 3 stars, it demonstrates that the universe still holds profound mysteries waiting to be discovered. Each new observation with the James Webb Space Telescope brings the potential for discoveries that could revolutionize our understanding of reality itself. The galaxy also represents the incredible power of modern astronomy to peer across billions of years of space and time, bringing us direct observations of cosmic history. We are not just passive observers of the universe's present state, we are cosmic archaeologists, piecing together the story of how everything came to be. Perhaps the most remarkable aspect of the GSNDG 9422 discovery is what it tells us about the nature of scientific exploration. In an age when we sometimes feel that all the major discoveries have been made, this tiny galaxy reminds us that the universe still holds wonders beyond our imagination. The galaxy challenges us to remain humble in the face of cosmic complexity, to stay open to possibilities we haven't yet considered, and to continue pushing the boundaries of what we think we know. It reminds us that every answer in science leads to new questions, and that the joy of discovery lies not just in solving mysteries, but in discovering that there are mysteries we never knew existed. GSNDG 9422 may be just a tiny dot of light in the vast cosmic darkness, but it represents something profound: the endless capacity of the universe to surprise us, challenge us, and inspire us to keep looking deeper into the cosmic mystery that surrounds us. In the end, this galaxy that broke physics has given us something invaluable: a reminder that we live in a universe far stranger, far more beautiful, and far more mysterious than we ever dared imagine. And perhaps that's the greatest discovery of all: